Welcome everyone to Temporal Difference Learning, and we're gonna see how we can learn by sampling from each step that we take. Now we have seen different types of reinforcement learning algorithms, and one is dynamic programming backup, which is computationally costly because we go to each and every possibility to get an estimate of the value of being in a given state S. Another way to do this is to look at only specific policies. For example, here this branch is going to be a policy, and we gonna go this policy, the whole episode, the whole trajectory, and then we go that multiple times, so perhaps one time, and we get a reward here. And another time, and then we take the average rewards as an estimate of the value function for that state. So that's going to be an unbiased estimate because we just, instead of taking the expectation itself, which we don't know what it is, we just take the sample average here, and that's an unbiased estimator for the population expectation. Now, this is going to be computationally costly as well because we need to wait until we run the whole episode. So is there a more sample efficient way to actually learn the value of a given state? And the answer is that temporal difference learning helps us to do this. So here we only take one step. We go from one state to the next state, and we receive a reward when we go there, and we can also check out what possible future rewards we could get from the next state. So here in every step we can actually update our estimate of the value function, and this is gonna turn out to be much more sample efficient. However, it's going to be also biased because we share here information for different policies. So we don't go the whole branch, but only part of it, and this part could be part of different policies. So we're going to share that information. That introduces a bias because we don't have for one policy the whole trajectory. But in the limit, it's gonna give a true estimate of the value of that state under some conditions that we take a look at now. So what is model-free evaluation? Well, we want to actually, for a policy, we want to estimate how good is it in terms of value to be in a state S without knowing anything about the transition model or the reward model. So temporal difference evaluation helps us do this, and the starting point is this value function for the policy pi for a specific state S. And here we got the expected reward given that we are in that state and follow a policy pi. Plus the discounted expected future rewards that we get in the future states. So this expectation here, this transition matrix, is the transition model, and this expectation, the conditional expectation on the rewards, is the reward model. And so we want to learn about this because we don't know that. So what temporal difference evaluation does is to take one draw. So we get one draw for an immediate reward, so one number, plus then the discounted value of the next state and the rewards that has. So that's an approximation to this number, and then when we repeat this, we're gonna get to a very good estimate of the value of that state under the policy. Now, to fix ideas, let's take a look at our grid world example. And here we had this policy already on the grid, but to just show how this step-by-step updating goes, let's zoom in and look at just two states and the transition between the two states. So we start in state S1, And we have been there already, and we went already to state S2. So we have a 73 here. That was our estimate for taking that action. Now, if we are in state S2, we have previously seen that when we go right, we get 100. When we go down, we get 81. And if we go back to S1, we get 66. Now, assume that we have a discount factor of 0.9, a learning rate that is 1/2. It could be a different learning rate depending on perhaps the number of times we visited that state already. And we have no, for simplicity, no rewards for non-terminal states. Now, the question is, what is the quality function of the state action pair here when we are in state S1, so here, and take the action to go right? So that's gonna be our previous estimate, which is the 73, plus the learning rate, which is 1/2, times an error correction. And this error correction is just the immediate reward that we get from going to S2. So we get 0. So R is 0, plus gamma, which is the discount factor, which is 0.9, times the maximum of all the possible rewards that we get from doing actions in S2. So what is the best here? We could go down and we get 81, but we could also go right, and that gives 100, and that's also better than going back to S1, the 66. So that's gonna be 100, the maximum of this. And then we compare this discounted expected reward here to our previous estimate, and that's 73. And so if we take the 100 times 0.9, that's 90. 90 minus 73 is 17. Then we take 73 plus half of 17, and that's 81. So if we are in state S1 and make the move to the right, then if we had before 73, we're gonna update our estimate for this to 81.5. So how this works is in our grid world example is like follows. So we have here our grid world example. We start in a lower left corner, and for each step we get some cost of minus 0.04, so 4% as before. And now we're gonna have for each action here a value. We initialize everything to 0. Now if I go up, we get a first estimate. That's minus 0.02. Well, our learning does also play a role here, and the discount factor. And so if we go on, then we end up and have an estimate for this terminal state of 0.5, now 0.75. If I go another one, 0.88, and you see also the other values are updated for each step that I take here. So I slipped and I ended up in the bad position. So the colors are relative, so you see they adjust, and we got here almost already the true value of 1 after a couple of episodes that I went. Yes, so here we got the 1, and if I go again to this follow the other policy and try to go to the bad space, now I slip a lot because of the noise, then there's gonna be also -1. So you see, by just taking steps we can learn the values of each state and each action. All right, so we can also use this to write it up as an algorithm. So the temporal difference evaluation is, as mentioned, an approximation of the value function under a policy for a given state. So we can write this as an incremental update. And that's just what we have seen before. So alpha n is the learning rate. And we have here the temporal difference target. That's the r plus gamma times the value function under pi of the next state. And so this gonna converge to a true value under the condition that the learning rate alpha does decrease, but it does not decrease too fast or too slow. So here the sum of all the learning rates in each step should go to infinity, so we should never stop learning. Otherwise, if we stop learning, if that alpha would be 0, then we do no correction anymore and we don't learn. So our value function doesn't change anymore. But also the square of those learning rates, if we sum that up, that should be still finite. So we should also learn less and less and less. So as mentioned before, the learning rate is typically the number of times we visited a given state. Now the algorithm looks like follows. So we can just execute a policy as we have done. We observe the next state and the reward. Then we update our counts and we update our learning rate, and then we update our estimate of the value function, and then we do that until we converge to a value for that policy. Now, temporal difference control helps us also to do more, to find the best policy, which is the goal of reinforcement learning. So here we take a Q function, and we want to get the best one. That's why there is a star. And that's the Q function under knowledge of the reward model and the transition model. But since we want to learn that, we are working model free. We just take this one draw approximation. So we just take the immediate reward and just the Q value of the next state. And then we take the maximum of it and discount this. Also here we can write up an incremental update, which looks pretty similar, only that we have here the Q values and the maximum here. And this is basically temporal difference learning. And compared to Monte Carlo evaluation, temporal difference evaluation has some advantages and is more popular because it's more sample efficient. It produces a biased estimate because it shares information, but it has a lower variance because you more often visit a state and you need less trajectories. Monte Carlo evaluation, on the other hand, is unbiased because it's just a sample average of the rewards that gives an unbiased estimate. It has high variance because you have few numbers of observations usually, and it needs many trajectories. So here's some references on temporal difference learning, and just to sum up, we don't need to know transition probabilities or reward functions. We can work model free. And temporal difference learning combines immediate rewards with an estimated value of the next state, which produces a biased value estimation from those bootstrapped samples, but still it's going to converge. The advantage is we revise in each step and we get more observations, so we need fewer trajectories, but there is still bias variance trade-off compared to Monte Carlo. However, temporal difference learning or TD learning is used very often in algorithms such as Q learning or SARSA. Thanks for watching.